Next, we're going to hear from Zaher Abbara. Zaher is such a promising student that he's got options to choose from. So he's currently choosing between either Cal Poly's San Luis Obispo or UC Santa Cruz this fall. It's changed a couple times over the course of the program, but he's got that much promise. He has an interest in machine learning techniques to help with education globally, and plans to use his engineering skills for video game design in the future. Zaher has been a great addition to his lab, assisting with a large-scale project being carried out in collaboration with Scripps. He's actually presented to those collaborators about midway through his internship, and when he talks to us today, I think you'll see why he was selected to do that. So please join me in welcoming Zaher up to the podium.
Thank you, Lauren. Thank you, everyone, for coming. So, today I'm going to be talking to you about utilizing phenotyping to study aging in mice using computer vision and AI. Quite a beefy title, but I hope we'll understand this in the end. My name is Zaher Abbara. I live in Los Angeles, but I moved here to San Diego to join the SURF program. I used to go to LBCC, Long Beach State College, where I took my GEs, and right now I'm pursuing computer science, hopefully in the fall. Right now I'm working with the Talma Lab in the phenotyping department, and I'm working on aging. So we have a problem. We need to study aging. It's quite difficult to study on humans because they have a lifespan of about 70 to 80 years, and you can have a whole team of researchers pass away before we can finish one study batch. So we need to use something else, and that's what the team from Scripps College, led by Professor Michael Petracek, is doing right now. Instead, they're using mice. Mice, they're a good alternative because first, they have a shorter lifespan, and they can easily be contained. And most importantly, they're genetically close to humans, so that even if we want to introduce medications or something like that, they can easily be extrapolated to human studies, and we can understand that better. But even mice have an issue when it comes to the human attention span, because we have very short attention span. We need to go to the bathroom, so you can't keep an eye on the mouse for the whole time. And we are inconsistent in recording behavior. And what I mean by that is, let's say we want to study rearing in mice, and what I mean by a rear is when a mouse goes up to its hind legs and start like sniffing the air or looking around. So one researcher might call this a rear, where the mouse is starting to get its feet up, but it's not all the way up. But another person might call this a rear, where it's already up, but another person might disagree with that because it's holding onto something, so they call it a supported rear. And my mentor quite literally said that he has very strong opinions on rearing behavior. So you have to solve this problem. And how we solve it is by using computers. It's quite a simple thing. You can just have a mouse in a cage, point a camera at it, connect the camera to a computer, and record a video, and you can start observing multiple hundreds of mice at the same time using very few equipments. But can create thousands of hours of footage, and it can create millions of files, and the researchers called it RRS, or Rodent Reality Show. That's actually a true fact. That's where we come in. That's where the Talma Lab comes in. This is the software we've been using. It's called Sleep, and it's an open source platform that helps with pose estimation. And it's working on it is quite simple. You just open the software, load the videos that you want to study, and then you create a skeleton for the mouse. And the skeleton is basically a couple of points that you want the computer to focus on. And over here we have about 11 pointers, like head, ears, nose, and like a couple of legs and feet, and the tail base. You then label these pointers on the mouse's body, and it would look something like this. This is a very low resolution picture, but you have to label every part as accurately as possible. You have to also consider that the mouse is not always going to be in this orientation. If it's running around, it can look like a different orientation, or it can even obfuscate parts of its body using its own body. So these parts have to be labeled as not visible in this frame, so that the computer knows not to consider these parts in the training later. Then we come to training. Well, you train, fix mistake, and retrain to improve results. And how you start that by going to this quite intimidating screen where the AI community likes to call it the knobs and dials of the neural network. Basically, you tune up the numbers up and down to fine-tune the results that you want out of the training process. And then you start training. It's quite easy to do, even with a simple laptop like mine. It can take long or short as large or small the data set you have. And the longer you train, you can see the more accurate it becomes, the less loss. And what I mean by that is the less difference between the trained result and the actual ground truth or the actual data that are labeled. With as few as 10 frames, you can get results like that, where the computer can detect parts of an ear, some parts of the body, and it's missing most of it. So you take these, you actually correct what's wrong, and you add the missing parts, and then you train again, and you get better results. And then you do the same thing, and you train again, and you get even better results. And what that leads you to get is eventually something like this, that a fully trained, fully labeled mouse can come out like this, which is a fully labeled mouse. This is all done automatically without intervention of a human. Well, after that, we can do this on the whole video, and that would give us something like this, where the left mouse can be running around, and the computer can, with sub-second delay, predict where the mouse is and pinpoint where each part of it is. And you can see it's doing quite a good job running around and with good accuracy. Well, great. We know where the mouse is. What can we do with that? We can do the same process again by labeling other objects in the cage, like this glass tube over here where the mouse runs in and out of it. We can also label the water fountain or the water spouts over here. There's two of them. And we can label the feeder. And then we can create, using some coding wizardry, something that looks like this, where you can see the interaction of the mouse with the environment, and the computer can tell where what the mouse is doing based on the cross-section of the mouse and the whatever area of the environment it's interacting with right now. That helps us eliminate the need for guesswork. So you can tell the computer if the mouse is running around that area for a certain period of time and it crosses a certain threshold, then that means it's drinking water. Same thing for the feeder, and same thing for the tube down here. You can tell the computer to detect these behaviors and then record them so that you don't have to guess if this is a feeding or a drinking or anything else. And that would lead us to the end of my project here, but this is only the beginning, I would say. You can run these. I only worked with around 50 videos or 100 videos, but the entire data set is about 120,000. So we need to run all this training on the entire data set, and then extrapolate these results to study not only mice, but humans, maybe other animals. And then writing the paper, I'll leave that to the team at Scripps. And I'd like to thank everyone from the Talmo Lab. That's Talmo. He quite literally held my hand through this entire project. Other interns, he's not a dog, he's a human, but he has a profile picture. And I'd like to thank the surf people, Lauren and Sophie. Thank you very much for your help.